Mhm. Audio testing, audio testing, audio testing. Hello, hello, audio testing. Yep.
All right. Well, welcome everybody to the first astronomy colloquium of the spring term. And today, Dr. Matthew Graham. Matthew is a research professor, as well as project scientist in CoPI on ZTF. And he's a Caltech lead for one of those big NSF AI centers. And I don't remember what they three. I can confidently say that Matthew is regarded as one of the leading researchers in the field of astroinformatics worldwide. And he's been involved in it since the very beginning. Arrived to Caltech in 2003. First as a postdoc, then staff scientist, and was involved in many different aspects of National Virtual Observatory, then Virtual Astronomical Observatory. Caltech, he moved up the ladder. He was task lead. He was project for that database scientist for two sky surveys, CRTS and Palomar Quest. So now he gets to do easy stuff. Yeah. And then without further ado.
Thanks very much, George. Good afternoon. So I'm going to talk about AGN variability today, and whether it's a Cornucopia or a Phantasmagoria. And one of the students said over lunch, only I would come up with a title like that, which I think is a good thing. But this is a very good subject for Caltech. Caltech, as we know, is the home of the discovery of quasars. Martin Schmidt took this first spectrum of 3C273 back in 1963. But actually, AGN variability predates that by a couple of years. So the 3C catalog of radio stars or radio sources was produced in 1959, and there were these very point-like stellar sources in there, which were very strong radio sources, and we started calling those radio stars. And 3C48 was one of those. And already in 1961, people started studying the variability of these to try and figure out what they could be. And there's this famous paper by Matthews and Sandage from 1963 when they're looking at what this could be, because they've got some spectra. And one of the things they note is that the most striking feature of these data is that the optical radiation varies. So we already knew right from the get-go that AGN, or what would become AGN, are very interesting in terms of variability. Today, we know that that variability is across the electromagnetic spectrum, and also they're sources of neutrinos and gravitational waves, and timescales from seconds through to tens of thousands of years. Interestingly, there was a good archival search for variability of 3C48 done in 61 already. This is the first example of an AGN light curve. So Smith and Hoffleit at Yale got their grad students to go over to Harvard and look through 2,500 photographic plates back to 1890s. And actually, it's worth reading the paper because there's a sentence in there describing with glee how they sent their students over to Harvard to do this work. And this is proper work for grad students to be doing, is looking through these plates. But the thing they came to is, well, there's maybe some variability, maybe not. It's hard to say from those plates because of the errors. And then there's this paper from Matthews and Sandage in 63 with, no, there is variability. But you'll note again that in the paper from Matthews and Sandage, they're looking at 11-year intervals, so they're already looking at these decadal baselines for variability. And in this case, they're using a blink comparator to say there's no zero motion, whereas these days we use machine learning. But this is not actually the first detection of variability of what we now know to be an AGN, because back in 1929, Hofmeister in Germany was looking at variable stars, and around Christmas 1929, obviously, whilst he's recovering from the Wall Street crash, he decides to look at the sky one night, and he notes this particular object. It's got a variability of a magnitude somewhere between 13 and 14, and the note just says that this is very red, stark, very red. So that's the first actual, this is a star, we think, and we now know that this is Bielac, a very blazer. So the variability has always been interesting. The question is, so what type of variability do AGN actually show? So there are three ways we can answer that. First of all, we can sort of say, well, okay, what's the theoretical standpoint for AGN variability? So our standard unified model of an AGN is we have a supermassive black hole in the middle. It's surrounded by an accretion disk of dust and gas, which is where we think most of the UV and optical radiation comes from. And then further out, there's this big, thick, dusty torus, which is where we get infrared radiation, infrared observations. And then surrounding there are these dust clouds giving us the spectral signature we associate with AGN. The broad lines come from clouds which are closer in, and the narrow lines come from clouds further out, and maybe there's a jet. And the standard model, this is the Shakuris and Yeev model, describes a geometric thing, optically thick disk, local viscosity gives you in-drift of material. We get various characteristic timescales for this, whether it's viscous timescale, stuff moving in, moving out, dynamical timescale, thermal timescales, and it gives us the overall steady state temperature profile of the disk as well, that the closer you get into the supermassive black hole, the shorter the wavelength of the radiation. So X-rays are in very close and infrared is around. Slight problem with this, it's completely wrong. And we still use it today, which is one of the problems of AGN studies. A lot of what we do theoretically and mathematically is just wrong. So this doesn't describe AGN variability. It's really hard for this to give us, and there are other things it does that gives the wrong size of the disk and all sorts of things. Doesn't tell you where you get X-rays and all sorts of things. But so that's our theory model. Or we could look at it from a mathematical standpoint. So the standard model that's used these days in AGN variability studies is this damped random walk or an Ornstein-Uhlenbeck model. This is, so if you take the simplest, so the idea is that AGN variability is stochastic. It's random in nature. And so therefore, if I want to describe that mathematically, I will use a stochastic differential equation. And the simplest stochastic differential equation you can do is what's this OU, and this is the solution to it. So it's a two-parameter solution. You have a characteristic timescale, which is where you get the bend and the power spectrum of this if you're looking at it, and you get an amplitude of variability. And just phenomenologically, it doesn't match with what we actually see when you look at data. And part of the reason is that Brendan Kelly, when he proposed this, used 100 poorly sampled time series, and we've got millions of time series these days. So we know it's wrong, but the thing is, it's simple, it's easy to calculate, it's easy to fit, and it gives you something that sort of looks like an AGN. And so for a lot of the purposes, you can use it to separate AGN with 80% accuracy, and if that's all you're after, it's good enough. But if you want to do detailed studies, it's not good, particularly because from a more technical standpoint, it's linear, it's stationary, so you assume that the mean and the variance aren't time dependent, it's reversible, so I can flip the time series around and it doesn't matter, and there are no trends in it. And all of those are things that we know phenomenologically that AGN do show, that they're non-linear, they're non-stationary, they're irreversible, and they do have trends, and so this is not good. And so, I should have put a reference in there anyhow. Ask me afterwards for the reference for that one. But it's not great when we've got millions, and there are more problems with it. You actually need probably at least 10 times, maybe 30 times your characteristic time scale to get an unbiased estimate. So if your characteristic time scale is a year, and you have an AGN which is a redshift of 1, you need 60 years worth of data to be able to recover that accurate, unbiased estimate that your characteristic timescales of a year. And so that's difficult with the data we have in hand. So the third way we can do this is actually, let's look at all this data. Let's look at AGN variability from the perspective of phenomenology. And to do that, obviously we need data, but we're very lucky these days because we've got all these wonderful data sets available to us, particularly here at Caltech. So a lot of what I've done over the last 10 years or so on AGN variability, I mean, these days, obviously, the winner is ZTF, hands down, but a lot of the groundwork, and still very important, is from the Catalina Sky survey, because you need these long baselines. 5 years is not enough, 10 years is not enough. Rubin is not going to be enough to do the studies we're doing now with the data we have in hand until the 2040s, when they've got maybe 10 or 15, 20 years baseline. WISE is incredibly useful. Atlas to some extent. Atlas is really useful because it fills in the gap between CRTS and ZTF, and so you can do these continuous data sets. And then Assassin can be useful, and Gaia can be useful at times as well. So we have all this data. So when we look at the data for AGN, what do we see? Well, there's a whole range of stuff that people report in papers. If you do an ADS search for AGN variability, you'll see all these words and all these sorts of different phenomena and whatever. So we can attempt to put these together into something that's sort of more meaningful. So we have, and on here is a mixture of both what we see phenomenologically and also what we might think a little more from a basis of theory or simulation, what we might see and that sort of thing. But we see, a whole range. So, Laurent did this famously for stellar variability, and so this is a translation into AGN variability. But we have these basic ideas that there are, this sort of stochastic variability that we're seeing. We're seeing these changing look things. And then there's all sorts of transients, and then maybe periodic and quasi-periodic things that we're seeing associated with that. So what this broadly translates into is that we know that AGN, in addition to this sort of stochastic burbling, do show more coherent behavior patterns. We know that AGN can get brighter coherently. These are the so-called changing state AGN, changing look AGN. So in this case, what they do is over 10, 15, 20-year baselines, they get progressively brighter, both in the optical and in the infrared. Those are the Ys. And when you look at what they're doing spectroscopically, you see them vary as well, that the broad emission lines get stronger. So there's obviously more material going on, or more material accreting. We also see them getting fainter, so-called turning off, or again changing look. And what you're seeing here is you see this very, very capable dimming, and then you see the Balmer lines just absolutely decreasing and a decrease in the continuum. Obviously, there are two explanations. There's either accretion, there's obscuration. We know that in most cases this is not obscuration because we don't see the associated behavior in the X-ray. So what we have is at least one of the things we're considering, or we have to consider, is that we're seeing changes in the accretion onto that supermassive black hole in a consistent or coherent fashion that this is all associated with. And then you've got to ask the question, what is it that's generating that change in the accretion? Is this just a regular thing, or is there actually some sort of triggering event which is then causing the larger scale dynamics of the material flowing into the supermassive black hole to change? Now, we know as well that things can get brighter and dimmer, and then brighter and dimmer again, and that's these claims of periodicity in AGN. We did a search for this back. So the idea here is that, and if you were up at the LISA meeting that's happening at JPL at the moment, you'll hear exactly a talk on supermassive black hole binaries and how those are important for LISA in 10 years' time. But the idea here is that we know that every galaxy has a supermassive black hole in the middle. We know that galaxies merge. So if two galaxies merge, what happens to their supermassive black holes? So you end up with a supermassive black hole binary, and eventually those should merge and emit nanohertz gravitational waves. We know that this actually exists because in 2023, Nanograv, or the PTA folks, announced the detection of the Hellingsdowns background in a stochastic gravitational wave background, which can only really originate from a population of supermassive black hole binaries. So we know that there exists. So the question is, Could we detect them? Well, if you've got two supermassive black hole binaries which are orbiting around each other, maybe you see some imprint of that orbital motion on the variability that you're seeing from them. So we did a trawl through, I think it was about 250,000 AGN candidates with Catalina data, about 10 years worth of data, and we found PG 1302 and 110 other candidates. So this is, fortunately, this is a really bright, well-studied object. So there is historical data going back. And so, right, so we got 1, 2 cycles, and then you maybe can convince yourself there's maybe 3 or 3.5 there. We put this out and it started a whole subgenre about this, and 5 cycles is the magic number. Because the problem is that damped random walk variability, red noise, generic red noise variability, which is how you model the stochastic nature of AGN typically, can give you the false positive signal of things that look like that. The question is, how do you distinguish the two? And it turns out that Simon Vaughan put a paper out in 2016 saying that if I have 5 peaks, that's really, really unlikely with a red noise process. So that probably is not red noise generated, it's something else that's generating it. And binarity may be one. More famously in ZTF, I think it's 3 years ago, was this detection from a Chinese group, the so-called TikTok source. And they were claiming, well, we've got 1, 2, 3, 4 peaks, and the time between each peak is shrinking. And so what we have here is a supermassive black hole binary that is going to merge in 3 years' time. And the press got really excited. This paper is still on archive. It has never appeared in a peer-reviewed journal. That tells you something. More interestingly, though, with this source is that when they looked at the spectrum, they saw significant evidence of change. And this is H alpha, and it's double peaked. So you've got a double peaked line. Those double peaked lines were an old idea about spectroscopic signature of binaries, and maybe that you would see that. However, a few years on, well, so this is the time range that they picked. They actually cherry-picked the time range they reported. They sort of said their signal should get shorter. There should be previous signal from it. Beforehand, Catalina showed nothing. And the thing is, this double peak signal you get from it is actually what's happening is you're picking up emission from the accretion disk itself. And so that's why you get that double peak feature. And there's a great paper called Panic at the ISCO by Charlotte Ward using ZTF data, who looked at a lot of the double peaked emitters, these so-called disk emitters, and they typically show 3 or 4 peaks in their time series. So they're a really good false positive. This is PG 1302. We now have 1, 2, 3, 4, 5 peaks. So, and there are a couple more if you go back to the dash data, but the calibration is difficult. So that's still looking like a really interesting binary source. Of the 110 other ones that we reported back in 2015, 10 years on, I can tell you that at least 90% of them are not viable. The periodic signal has not maintained. So this means I need these really long baselines to get enough signal to figure out what's going on. They are still interesting because what is it that's giving us these quasi-periodic signals, but whatever. But what this tells us is that we really need good models of the underlying variability so that I can assess something unusual to say, is this what I think it is? Or is this, how rare is this phenomena given a very large data set? Can I put a statistical measure on it so I can say, this is something interesting or this is something not interesting? So a lot of what I've been doing in the last few years is sort of applying deep learning to AGN time series on the hope that it actually does better than the statistics. So Yutaro Tachibana, whose thesis I helped co-supervise, was here just before the pandemic. And Yutaro did this wonderful idea that we started applying. This is a recurrent neural network, which is a deep learning model, which is very good for time series. And what we actually do is a recurrent neural network autoencoder. So what we're doing is we're taking our long time series, and then we map them down to a much lower dimensional latent space to see if we can track characteristic signatures of variability in that much smaller space. So we did it with Catalina data just because we had the baseline again, and about 12,000 quasars. The other thing we were actually interested in doing was, can we predict future behavior of AGN so that we could then do monitoring with ZTF to see if this is going where it's going. And we got some success with that, not enough to actually win on the stock market, unfortunately, but because if we can do it for AGN, we can do it for the stock market, is the theory, because it's stochastic, right? Different types of stochasticity, actually, but that's another talk. So we mapped it down into this low dimensional reckoning, and then we sort of said, okay, so here's a two-dimensional sort of idea of what our 16-dimensional latent space looks like, our low-dimensional manifold. And is the mapping meaningful? Well, in terms of, if you were thinking about a shapelet decomposition of your time series, or what are the common patterns that I see in terms of rising and falling, it does turn out that different bits of this parameter space or different bits of this latent space do correspond to sort of different patterns that I might see in the data. So there is some meaningful mapping into that. And in fact, if we take these representations and then think of them as features for variability and see how those correlate with black hole mass or Eddington ratio or other physical properties we know for the AGN we were looking at, it turns out, yes, there is physical information encoded in this latent space, because ultimately that's one of the things we want to do from the AGN time series as well. It would be great if we could use a time series and get what the black hole mass is, or we could get the redshift from the time series alone. So the information is encoded in here, but it's not a simple encoding. It's actually smeared over those 16 dimensions in this particular case. So the question then was, with this work, we demonstrated that we could take variability and do stuff in that latent space with it. Is our latent space not complicated enough? We go down, but what actually if we go the other way and think about an infinite dimensional latent space? And in fact, what we're doing here is, you remember the damped random walk makes that assumption about a stochastic equation which describes the AGN variability. So, but what I'm trying to do when I'm just fitting it is too simple. Now, what happens if it's that stochastic differential equation is describing the variability or the behavior in this perfect latent space, but what I actually see here, there's some observation function on it, on top of that latent space, which gives me my variable. So my data is here, and it maps into this hidden space where the behaviors can be described by a continuous time representation. But when I take observations, I'm just looking at individual instances. So what I can do is I can model the evolution of my latent space through a stochastic differential equation, and I can put a neural network around it to learn the mapping from my real data into that latent space. And that's what these latent stochastic differential equations are about. And Josh Fagan, who's a grad student in New York, and a couple of other of us have been working on this for the last couple of years, and we put a paper out on this last year. And then, because they're coming from the theory community, they're sort of saying, well, what we could do is we could actually encode, we could simulate light curves where we know what the physical parameters are, and then for the X-ray, and then do photon reprocessing through the disk, transfer functions, and all that. We can encode all the physical parameters into those light curves. We know what the answer is. And then can we put those through the system and recover those in this? And so we've demonstrated this in another paper last year, that we can sort of do that. So the idea is that we have shown with simulation that with this sort of very complicated network, we can recover black hole mass, we can recover redshift, we can maybe recover corona height or X-ray strength from the time series. And that's very much looking at sort of Rubin type things. So our modeling in that sense is getting really good. We still make an assumption with that one we still feed, I mean, we still have to model what the X-ray variability on the corona is, and there's an assumption made there. But the ultimate one that we want to do is actually, what happens if we could actually learn the stochastic equation that's driving this? And Pavlos Protopapas, who was here a couple of weeks ago, gave a very good talk about these pins, these physics-inspired neural networks, and or physics-informed neural networks. I always call them inspired, but they're informed. And the idea here is that I can put, I can model my system, my neural network, in such a way that it encodes physical information about the system. Here's an example. If I was modeling a simple harmonic oscillator, there's my standard differential equation for an SHM, and here's my loss function for a neural net. So there's my irregular term, and then I add an additional term, which is saying how well does what I do with the differential equation. So what I can do is I can actually model up my neural network. I could replace this with a stochastic differential equation with general diffusion terms, and then learn the differential equation that's making my data done. And then on top of that, there's a technique called symbolic regression, which will then give me an analytic solution. So having trained my network, I can fit it to a data set, and then I can get an analytic expression back, giving me the perfect answer of what it is that we're doing. And so we've got an NSF proposal in on this, and we've got at least a conference paper going to NeurIPS. I think it's NeurIPS later in the year on this. So this is the absolute state of the art. If we could do this, then that would be brilliant. We also have been applying some of these techniques to ZTF data, and Szymon Nekoneczny, who's just left as my postdoc, he went back to Poland. He's been working on the ZTF AGN catalog. So we use these transformer things. That's the technology underneath large language models for doing really good time series modeling on ZTF data. And he ran it through almost 1 million light curves, which met our criteria. And we've got 5 million AGN candidates now, high probability AGN candidates in ZTF from this. And that's a wonderful data set to be working from here on in. So we've got good models which we've learned from the data, but the problem is still in a lot of I mean, this is general variability stuff. What it's not factoring in is it's still, really thinking about, I've got a supermassive black hole and I've got an accretion disk around it, and that's all that's going on. And what it's not taking into account is the environment. And we know from the Milky Way supermassive black hole that there's a nuclear star cluster there. I've got stars going around it. I've got black holes going around it. I've got dust clouds going around it. And if I shove an accretion disk on top of that, they're all going to be interacting with that accretion disk. And our models don't count for that. Now, one example why this may be important is this thing that we did in 2020. LIGO was putting out things, and for various reasons, the most massive stellar mass black hole mergers that LIGO detects probably live in the deepest gravitational potentials out there. And you find the deepest gravitational potentials around supermassive black holes. And if that's the case, you've got a stellar mass black hole merger that's happening in a very rich, dense environment. And so therefore you should get an optical signal when that merger happens. And we thought that, and we said, well, let's look. And so we found this one. So this is 1905-21G. This is when the LIGO event went off, which is that thing up at the top. 30 days later, we got the signal. Now, one of the advantages of this, or one of the differences about this from kilonova, is that when kilonova happened, the thing goes off, boom, and every piece of big glass on the planet or big dish on the planet goes and looks for the signal. This takes time for the photons to get out from the photosphere because it's happening in the accretion disk. And so it's a much longer game. So we saw this happening. We did a mass estimate and we said, oh, right, this is probably from a 150 solar mass system. We published that, and 3 months later, LIGO said, oh yes, 1905-21 was a 150 solar mass system merger. We should expect to see a spectroscopic signal because you get off-axis illumination from this, but we got on it 200 days later and we didn't see anything, which is what we would expect to see, but it's a null detection, sadly. And we've got monitoring programs going on now in 04, and Kira Nolan, my postbac, is working on this, and we're trying to find things. I can talk more about that. But those are the smallest flares. Those are interesting. But the thing that sort of grabbed attention more recently was 2 years ago, Scary Barbie. So this is ZTF20 ABRBIE, so-called Scary Barbie, because someone looked at the name and said, oh yeah, that's Barbie, and Barbie had come out, and yeah, anyhow. So this is ZTF data they detected it in. This is at a redshift close to 1, and it's absolute magnitude of minus 25.7, total energy of about 10 to the 53 ergs. For comparison, tidal disruption events sort of peak around here, supernova peak around here. So what the hell's giving me the energy to drive this thing? When they looked at it spectroscopically, they see a Balmer series, they see low ionization lines typical of an AGN, but they don't see any O3 emission at 5007 angstroms, which is a typical narrow line that you see in AGN, which does not change on human timescales. So what that's telling you is that this is a supermassive black hole that has been quiescent. There was a WISE echo, so you're getting reprocessing by that dusty torus, but there was no prior WISE data. So this tells you that, again, this system has been off for a long time, if it's actually ever been on. So just a reminder about tidal disruption events. So my star comes in, it has an orbit which brings it very close to the supermassive black hole, it gets pushed out, and if it's within a particular radius, it will get shredded. Half the material is bound, the other half of the material goes away. ZTF has been really good at finding these. As a general rule, the people who look for TDEs in ZTF say, is this an AGN? If it's an AGN, we're going to throw it away because that's noise and we don't want to deal with AGN variability, it's too complicated. So they're looking for TDEs mainly in quiescent galaxies. We've got about 100 of them now, named after various things. We found 4 spectroscopic classes. So the typical mass of the supermassive black hole is 10 to the 5 to the 10 to the 8. If it's higher than 10 to the 8, the star would just go straight in there, and you get direct capture. And typically the stars themselves are in this 0.2 to 1 solar mass regime. Now, the thought for Scary Barbie was, when they do the fit, okay, well, it's at the high end in terms of what the black hole mass is, but what happens if it's a more massive star? What if it's not a 0.2 or a 1? And so they fit it with MOSFET, I think it was, and they get that it's a 14 solar mass star around this thing. And then there's another group who said, or it's a giant molecular cloud. Yeah, okay, whatever. So we started, I mean, we had actually been tracking this one, and just as an interesting big AGN flare, because we've got lots of them, as I'll show, but we hadn't done much with it more than that. But we looked at some of our other ones. So we've got this one. So this is a redshift of slightly closer. I mean, it's 0.7, but it has a Balmer series. It has low ionization. It's semi-forbidden. It has no O3 again. So this tells me I've got a system that's very quiescent. We have a WISE echo, and there is prior WISE data on this one. And what that tells us is that it has probably been on in the past, but it's sort of very quiet now. And when you do the MOSFET to this, okay, so it's a 7.8, 10 to the 7.8 mass supermassive black hole. And again, it says it's a 15 solar mass star. And you go, okay, Well, it turns out that there's a slight problem with MOSFET. MOSFET was not designed to fit things like this. And so you get it converges on these stellar masses. The current thinking, actually, and Jason Hinkle from University of Hawaii was here, I think, a few months ago, and he put this paper out last year. So this is the landscape in which a lot of the very brightest transients or AGN things are sitting. So here we have tidal disruption events. So we've got decay time, the time it takes to get to half the peak luminosity on the x-axis, and we've got peak absolute magnitude on the y-axis. So core collapse supernova here, tidal disruption events here, superluminous supernovas. You can see there are these things called ambiguous nuclear transients, ANTs, which we don't really know what they are. Changing look AGN could be in there. Tidal disruption events could be in there. These Bowen fluorescence flare sources you may have heard about are sort of sitting in there. It's a nuclear transient of some description. They're quite energetic, but it's probably a heterogeneous class. And then there are these three objects up in the top right, which are called ENTs, which are extreme nuclear transients. And that brightest diamond at the top is Scary Barbie. And so the idea is, okay, here are my regular tidal disruption events. Now I've got one or two tidal disruption events that are very bright, that have been discovered in the last couple of years. And these ENTs are probably maybe associated with something which is not exactly a quiescent nucleus. Maybe it's a slightly weak AGN, but they're stars in the mass range of probably 2 to 10 solar masses. So my 0.2 to 1 solar mass TDs are here, and then my more massive TDs are there. And when we've done, so we published a paper back in 2017 saying here are a whole load of massive AGN flares from Catalina, and we've updated that now. And so we've got a whole load of sources that are living in that ENT area that to be looked at and understood and probed. But more interestingly, there's an old transient, which we looked at again, which is appearing up there, outside. I mean, you know, that's a magnitude and a half brighter than Scary Barbie. So we initially called this Ken, or just Ken, because we were looking at it at the same time. So, but this thing is at a redshift of 2.5. Okay. So we benefit from a factor of 3.5 in time dilation. The spectrum shows Lyman alpha semi-forbidden line. So this is an active AGN. This is definitely on. There's a Wise echo, prior Wise, and the mass of the thing is quite high as well. And for a variety of reasons, we changed the name from Kent to Superman, because we don't know what this is. Is this a TDE? Is this a supernova? Is this gravitational lensing? Don't know. You know, is it a bird? Is it a plane? No, it's Superman. Well, in this case, it's Superman. So we've been studying this for the last year or so, last year and a half. So here's the optical. Now, the real good advantage of this one is that there is prior pan-stars data, and we can do deep, there's some Atlas data as well. So we know what the magnitude is before the flare goes up. So ZTF started here, right? ZTF is here, is just pre-peak. So this is ZTF 18 something something something. It's a very early transient, and ZTF never got it because it was very, very early on. Actually, it was detected before we started the official ZTF alerts. And you see it's gone down. Now, fortunately, Catalina had detected it, and Andrew Drake had flagged it back in 2018, and we got a spectrum of it in November 2018, and it was noisy and it was crappy, and we thought it was a blazar, and we thought, nah. And then 5 years later, Andrew sort of said, you know that thing that went off 5 years ago, it's doing this. Oh, we should look at it again. And we did. And then this is where we realized it was at redshift 2.5 rather than whatever and whatever. So this is KCWI data we got last year for it. This thing here, so we initially saw this in LRIS imaging, and we thought, oh, right, okay, this is gravitational lensing. We've got something along the line of sight. However, it turns out that this blob here is at the same redshift as the rest of it. That's the position of the nucleus. That's the position of the transients. So this is some, extension of the galaxy, of the host galaxy, or something like that. The red dot is where there could be a putative sections, but we know there's not one down to at least 24th magnitude. So it's not gravitational lensing, and it's not a supernova. So what the hell is this? This thing gives off a total energy of 10 to the 54 ergs. There's very few things that give you that amount of energy, and it's still going, and that's only in the optical. It's got some radio detection beforehand, but nothing changed. There's no X-ray detection from it. It's very difficult to figure out what it is. Spectroscopically, well, so this is the original crappy spectrum we had. This is spectrum we got then as well. So it's obviously, there's more energy pumping in. The emission lines are getting stronger. There's evidence of outflow in the Lyman alpha and the carbon 4 lines. There are absorption lines along the line of sight. We thought one of those may be the lens, but no, it doesn't work. So it's a very interesting source. It's a classic AGN putting out a huge amount of energy. Now, stars in AGN disks are really, really interesting because stars in AGN disks behave very differently than stars in the field. In particular, if you have a star sitting in an AGN disk, it has an initial period of very massive accretion. And depending where it is, okay, ones that far out, you get canonical stellar evolution. But if you come in closer, you can get massive stars, and then you can get these so-called immortal stars, which are fully convective. They go up to about 200 solar masses, probably. And then there's a regime where you get runaway accretion. But in terms of things that these can produce, maybe these are going to develop into intermediate mass black holes, 500, 1,000 solar masses and sort of thing. You may get GRBs and supernova happening out there. And here you may get collisions between these large stars and compact objects that are the remains of regular stellar evolution further out. But there is this population of stars, and in particular, this is predicting a top-heavy IMF. So I'm going to have a lot of massive stars and out in this regime. And it turns out that when I look at what sort of star I need to do a tidal disruption event to explain Superman, it's maybe it's in the 40 to 100 solar mass range. And so our theory friends are telling us we should find a population of those stars there, and we have at least one TDE in an AGN disk, which seems to be showing that. So there's some interesting stuff going on. And actually, it turns out that these TDEs that are happening in the AGN disk are really interesting. So our regular TDE just gives me something that looks like that, right? But if I've got a disk there with material, I can have a star coming in the same direction as the disk of material is rotating. So it's a prograde injector, or I can have it coming in the opposite direction. So it's retrograde. And that means that when it falls in, that material is going to be shredded, and it's going to be going against the flow of what the regular accretion disk is going to do. And there's going to be cancellation of angular momentum, and that's going to get dumped on. And then that's going to create a cavity in my accretion disk. And so depending on whether I'm looking at a prograde or a retrograde tidal disruption event in an accretion disk, with an accretion disk, I should see a different type of behavior. So if I'm prograde, I've got the regular behavior of the AGN before the tidal disruption event. The star gets shredded, and then it goes back to a higher level because there's more material coming in, and that's being dumped in on that central. And that's what we sort of see with Superman. If I have it going the other way, though, if it's a retrograde system, I should actually see the tidal disruption event go to a lower level because I've got less of my accretion disk post the tidal disruption event, and I've got a cavity system there. And so the most exciting one we're looking at the moment is Iron Man. So this went off in 2003. and it goes down, and it goes down below the level beforehand, and it sits there for about 10 years. And then ZTF starts, and we get a repeat flare back to the level it was before. So this shape looks exactly like the shape that our theory friends are saying that we should see for these retrograde. And we've actually got a number of these. Now, what's even more interesting about this one is that I also have repeat flares. You get these with partial tidal disruption events. So the star is not necessarily fully shredded. It's partially shredded, and then it gets repeated shredding on repeated orbits. So what we have here is a very plausible partial tidal disruption event, retrograde, in an AGN disk. And what's also interesting about this particular source spectroscopically is we have spectra at 2008, 2016, 2024. So this is the actual Sloan spectrum, is that there's a lot of ion emission in the optical, which is very like PS16 DTM, for those who know their telephone numbers. So the question is, where is all, and we're seeing evolution of the ion emission with time. And so the question is, where is all this ion coming from? Which is why we've called this system Iron Man. So this may be something to do, okay, it's plausible it's a narrow line Cepheid-1 galaxy. Those can be ion rich. We don't know why. You get boosting of the ion emission if you have microturbulence. Maybe what we've seen is that the retrograde gives you more choking up of material as well. That gives you an initial boost to the ion emission, and then it's fading out. And we see this with PS16 DTM as well. But you need long timescales to see all this sort of thing decadal, which we've got. So we've got 20 years on this system. So there's some very interesting stuff going on with these very large flares, which are telling us about interactions with things going on in the disk. So where are we? Well, we're not happy enough with ZTF. Rubin's going to be useless for 10 years. What can we do? We can do better with ZTF for archival stuff. There's a growing appreciation in ZTF for force photometry, not just the stuff that IPAC puts out. I mean, the stuff that IPAC puts out is great, but what if we have force photometry for everything in ZTF? So Tom Prince and I have been leading an effort for the last year or so. Andrew Drake is doing a lot of the heavy lifting on this for ZVAR. And the idea here is that we already have now a data set of ZTF force photometry at every pan-stars 1 position. So that's 3 billion force photometry data points. What's useful about that is the nominal survey limit for ZTF at the moment is 20.5, but this pushes it to 22. So we gain a magnitude and a half, and so there's a much fainter, further away, deeper data set that we can do. We're now expanding this even further by dropping pan-stars as the source catalog where we're looking for things, and using what we're calling the ZTF deep catalog, which doubles the number of sources where we're going to be getting force photometry. And Andrew is also doing a lot of work on correcting the photometry, detrending it. So we're getting really accurate photometry as well, correcting for proper motion. So this is going to be a beautiful data. The stellar variable folks are very excited about this because they can find periodic binaries down to 22 at least, and maybe even further. I'm very excited about it because I think there's a lot of AGN that are just sitting there waiting to be discovered and increasing the data set that I've got available to me. The other thing that's coming on with Ultrasaturn and UVEX is UV, and I think this is going to be really important for AGN variability. First of all, for new phenomena that are most likely to occur in the UV, so a whole load of quasi-periodic stuff. Stellar collisions in the AGN disks are supposed to produce short-lived UV flares. Maybe there's UV microlensing. There are wavelength dependencies for supermassive black hole binary models, and then there are changing look where we expect the UV continuum to drop and recover as well. Whole load of interesting stuff, and obviously UVEX is the thing we're most excited here about, and that's going to be really good for a lot of this stuff. I think there's a lot of interesting stuff coming along the line that's really going to help us. So I'd say we are looking at a cornucopia more than a phantasmagoria. So AGN show this vast range of phenomenology, and it's related to the supermassive black hole, but more importantly, the accretion disk and what's happening in the accretion disk with these different populations all interacting. And that's what's different from what, Matthews and Sandage or even Brandon Kelly were thinking about then. Most of our information comes from optical time series and spectra, really important, but historical records are really important. This is a scientific long game. This is slow phenomena. Something happens and it can take a long time, particularly multi-wavelength. We know that TDEs are now interesting because maybe their radio stuff is doing 5 years after the TDE has happened, or things like that. So we need, okay, everyone's thinking about the next big data set, but we should also be thinking about how do we preserve the archival data we have and make it usable. Most of our methodologies are not based on modern data. We can do better about that, and things are looking bright. And especially for Sri, who always calls AGN weeds. I gave ChatGPT that I write a poem about AGN variability for someone who considers them to be weeds. So they call them weeds, these flickering lights that blaze and dim on cosmic nights, and nuisance some astronomers say, yet watch them closely, don't look away. AGN dance wildly, never still, a cosmic heartbeat, a primal thrill. Their glow pulsates in mysterious rhyme, revealing secrets of space and time. From black hole cores, they fiercely roar, changing yearly or daily more. Their variability speaks loud and clear, echoes of physics we long to hear. Not weeds at all, but gardens wild. Dynamic wonders, chaotic, beguiled, each flicker tells of energy vast, secrets hidden in their luminous blast. And their brightness shifting, fading bright, lie answers veiled in cosmic night. They challenge minds, inspire dreams. AGN teach more than first it seems. So pause a moment, give them heed. See in their dance not just a weed, but excitement, wonder, intrigue, fun. AGN variability's radiant sun. Yeah. So part of the problem is we don't know, in the sense that our knowledge about accretion disks is not good. We have maybe one or two, I mean, EHT is helping. We got some examples there. There are more sophisticated models. There are models where you actually have there's the lighthouse model where you have the X-ray corona, then you have the advanced lighthouse model where you have the X-ray corona and magnetic fields, which are coupled into all sorts. I think Phil Hopkins has a different model, which seems to be more closer in some regards to what we're seeing. Simulations are getting better, but these are, the problem is that these are, you need general relativity, you need MHD, you need blah, 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 vast different scales. These are difficult things to model. So we're getting there, and I think we're in a much better situation. But yeah. Yeah, no, and so there are more sophisticated analytic models that you can use for what the disk profile is and things like that in the literature. The problem is that, as with the damped random walk, for a lot of what you're looking at, it's good enough. And then people are doing more sophisticated analysis on an assumption they think is good enough, but it's not, because they're trying to infer things that may be a consequence of an assumption in that model rather than questioning what they're doing from first principles. Yes. I'm trying to remember. There may be. But I would say that, I mean, work that we're doing and that I'm doing at the moment is we're trying to build these samples of things that look like retrograde or prograde in the disk. And we should be able to infer a lower limit to a possible rate from there then. And then I think, again, the problem is we don't know. Again, the problem is we don't know what the stellar population numbers in a disk are. I mean, you make an assumption about the disk, you make an assumption about where the seeds are coming, all this sort of thing, and you can run that simulation, and you've got one example of a simulation where you've run that. And to do that over the whole spectrum, I think, is computationally expensive, and they're not there yet. You know, a lot of these things just run in 2D as well, as you know, and so, you know, this is very active and very current, and I can show you 5 papers in the last month where they're doing things with this. But it's, yeah, we have a better chance of being informed by observation with the data we have in hand and going back through the archives and going, okay, if I have 20 years of data, let me go through and see, and then following up those to create those samples. And then those can inform the theory rather than looking at theory per answer, I would say. Yeah, I don't know. I can't remember. Maybe. I mean, we've seen one or two sources which seem to, they have a flare, and then maybe there's a helium. We see temporary helium lines in the spectrum, which then fade away, which some people have speculated could be the case for one of these immortal stars, because they can just be dumping a lot of material in, depending, or also, you know, some AGN shows super nitrogen abundance, and people have speculated that that could be coming potentially from the stellar population. But I don't think we have, there's not been enough follow-up work or connecting the spectra with the variability on those samples yet. I think we have the data in hand, not just with the stuff we've done, but I mean, if we take all the DESI and the Sloan 5 spectra and find those sources and then look what their variability is done, I think it is easy enough to create the data sets that would inform you either way about whether there's stuff in there. I think with the one of the ideas with one of the TDEs, which shows iron abundance, not Iron Man, but one of the other ones in the sample, is that there seems to be a change in the IR response. The idea there is that there may be sublimation of iron that's coming from the dusty torus in response to the TDE burst that's going on. But so you're releasing more iron, so you're increasing the abundance from that. But I mean, I actually prefer the microturbulence because that's a much better understood mechanism for, at least for UV Fe2 emission. And I think that's true with the optical as well. I think that's what we're seeing. It ties in more with the dynamics of these retrograde systems, and that you're increasing the mixing that's going on, at least for a while, and so boosting resonance mechanisms. Yes. Yeah. Yes, I mean, there is. So when you look at QPEs in binary star systems, you tend to see 2 modes. You see a high frequency mode and a low frequency mode. And what we're seeing in the AGN systems in the X-ray is the equivalent of the short timescale mode. Potentially, there should be a longer timescale mode as well, which might show up in the optical. And I don't think we've particularly looked for that. So I think there is, but the idea is that that 100-day timescale oscillations you see in the optical probably would be linked to QPEs. I was having a chat with our Monday Tea Talk speaker about with Jaheen, right? So it's possible because you see this in the binary X-rays, and so if you scale everything up, the QPEs we see in the X-ray are the equivalent of the very short time scale, and then you should expect to see something that maybe, but it's possible. I mean, it depends on the mass of the star and where it's interacting with the disk and things like that, I think is the issue. Yep. Yep. Yeah, no. So a lot of people do. So a lot of the changing, for example, a lot of the changing look AGN that people have studied are, they're Mercarian systems, or they're really nearby low redshift where they have the time series. So they've got 30, and these are bright, right? So they've got 30 years worth of data, and they see it does this. And if this was at redshift 2, we'd need 100 years worth of data to do that. I think the problem, again, it comes down to that's a single system, and we can do really good modeling of it, but it's still a single system, and there's enough variety in the potential. I mean, we haven't talked about disk orientation, and there are some ideas that maybe I have the inner part of the disk may be rotating this way, and the outer part is rotating this way, or I have warp disk, and all this sort of thing going on. So I think there's a rich set of phenomenology, and we need a lot of data to get good samples of everything that we're after. And the CFATs give us good individual examples, but to understand the phenomena or the range of phenomena, we would need more, unfortunately, and we don't have that. But yeah, I mean, there's the nearby stuff is good because we can see what's going on, and maybe we can resolve certain systems, or we can measure more easily than something that's sitting at redshift 2.5, and we need a space telescope to look at it properly.